All right. We're going to start Chapter 7, Lesson 7 today. But before we do, I want to review a couple of things. First, I want to review exponential functions. The basic form, y equals ab to the x power. All right. A is the starting value. B is your growth or decay rate. X is units in, often it's time. And y is what you end up with later. We had another form of this equation that we didn't talk that much about. We did a little bit. I'm going to talk about it a little bit more right now. And it was in the form a of t equals some starting amount p times 1 plus r over n all to the nt power. All right. This is similar to the equation above, where your starting value is p, and if we're talking about money, that'd be your principal amount of money, what you start with, and you invest it over a certain amount of time, t, and you end up with some value later on, right there. All right? Well, let's talk about this part. All right? That, in the other equation, is your base. Well, here we have 1 plus r over n all to the n power. We used this, we talked about it a little bit, where the n, well, the plus, first of all, if you have a plus, you're talking about growth. And r is usually your rate of growth, what percentage of increase, 2%, 3%, or something else. The n was the compounding, how often something was compounded. And the example I used was with money. If you invest money and you earn interest on it, which is a good thing to do, the more often that you get to take the interest that you earned on your money and put it back in with the principal amount of money so that you can make interest on that money, the more often you can do that, the faster your money will grow. And that's what the n represents in this equation, how often you can do that per year. If you can compound your money monthly, that would be 12 times a year, and would be 12. All right. If it was weekly, and would be 52, and so on. Well, today's lesson is going to talk a little bit more about that. Here we go. Chapter 7, Lesson 7. Base E and natural logarithms. So, as n increases, here we are, as n increases, the expression 1 plus 1 over n to the n power. That's the part that we were just looking at. As n increases, this value doesn't grow and grow and grow and get bigger and bigger and bigger. It actually approaches a certain number, and that number is irrational. And it starts off with 2.71828 and keeps going infinitely without repeating. And in math, this number is called the natural base, and we designate it by the letter E. E is not considered a variable or a letter, it's considered a number. You can think of it as similar to pi. Pi technically is a Greek letter, but in math it's not a letter at all, it's not a variable at all, it is a value, and it's an irrational number. So E and pi are similar in that respect. Since E is bigger than 1, if you were to take it and put it into an exponential function right there, that would mean the base E was bigger than 1, and then this expression would be considered exponential growth. And this is considered the natural base exponential function when the base is E. Now, E is the number, again, 2.71828 and so on. That's the number you get when we increase the n and have it get larger and larger and larger until it approaches infinity. All right? We talked about if n was 12, it'd be like compounding monthly. 52 would be compounding weekly. 365 would be compounding daily. And as that number gets larger, you could be talking about compounding hourly, minutely, secondly. But even more and more, as that approaches infinity, what does that really mean? You're compounding, as you're approaching infinity, it means you're compounding continuously, all right? And that's common in nature, actually. Natural base exponential functions are used extensively in science to model quantities that grow and decay continuously. For example, cell growth, plant growth, or decay, the movement of things. You don't have, when things move, it doesn't start at 0 and then a second later it's at 2 feet. It actually has to get there. So it has to travel the entire distance. It will at some point in time be at every distance from 0 to 2 feet. When a plant grows and it starts as a seed and say eventually at full height it's a 20-foot tall tree, to get to 20 feet it had to be every height in between 0 and 20 feet. It doesn't just jump. Okay, it can grow fast, but it can't just jump. That's continuous, all right? And so it's continuous growth is very natural. So it's going to be used in a lot of real life situations. All right, let's move on to a little bit of practice. Well, the inverse, just like before when we talked about inverses, the inverse of an exponential function is a logarithmic function. Here we have the natural base exponential function, and if you switch the x and the y, it looks like that. And the way we talked about that before is that's one of two ways to write a logarithm. All right? This is called the natural logarithm. All right? And it can be written in its other form, just like other logarithms can, in its logarithmic form, where you have log, write your base, which in this case is e. So log base e of x equals y. Now, this is a special case just like common logarithms. Remember, common logarithms were abbreviated and you didn't write the 10 as the base. Natural logarithms are also abbreviated. Natural logarithm will just be an ln. You don't have to write the base e. So natural log x equals y is the way you'll typically see it. The logarithm ln actually comes from, I think it's the French, logarithm naturale. I'm close, I don't remember it exactly, but that's why it's ln, natural logarithm. You'd think it would be nl, but it doesn't come from the English, it comes from, I believe, the French. All right, let's use our calculators. Oops, here we go. Use a calculator to evaluate each expression to 4 decimal places. All right, I put in a little picture of a TI-84 here to help out. All right, so find your E button and your e to the x button and your natural logarithm button on whatever calculator you use. For this calculator, there's e's exists in a couple places. It's over here in blue, so it's a second function. And that's if you just want to put the number e in. Or over here, right there, e to the x power. So if you want to do like the first two, if you want an e to some exponent, you could put it there. And that is the second button to, right below it is the ln button, which so you could do the numbers 2a and 2b. That's the natural logarithm button. All right. So you could pause real quick and try and put all these 4 values in and go ahead and write them out to 4 decimal places, and then I'll write the answers and you can check. Okay, here's the values you should have. Go ahead and check those to make sure you're using your calculator correctly. All right, let's move on to some more examples. Write an equivalent exponential or logarithmic equation for each of these. All right, the first one is not written in logarithmic form because you don't see the word log there. So let's change it to logarithmic form. We're going to write the word log our base is e because there's our base. Logarithms equal exponents. In this case, the exponent is x. So the answer is log base e of 23 equals x. Now, what do we say about log base e? It is typically written as just natural log of 23 equals x. Okay. Natural log of 23 equals x. Let's look at the next one. The natural log of x is approximately 1.2528. That's in logarithmic form. Natural log is base e. Just think of it as a little e there. So when we write this in exponential form, we have x equals e to the 1.2528 power. Okay? The base becomes the base over here. Okay? Logarithms equal exponents, so the 1.2528 is the exponent. All right, now let's solve some problems using what we know about logarithms and e. Okay, let's solve this problem. All right, let's isolate the x. First, let's move the 4 over. Let's subtract 4 from both sides. All right, let's divide both sides by 3. Okay, now let's use what we know about logarithms to solve for x. We could write this in logarithmic form. All right, let's do that. Let's write log. The base in this equation is e. All right, we're going to equal the exponent. The exponent in the equation is negative 2x. So log base e of 2 equals negative 2x. Well, log base e of 2, another way of write that is natural log of 2 equals negative 2x. All right. So how do we solve for x? All we need to do is divide both sides by negative 2. Those cancel, and x equals the natural log of 2 divided by negative 2, and when you use your calculator, you will get negative 0.3466. Now this is rounded, so this is approximately, that equal sign should be squiggly lines. It's approximately that, and that's what you should get. All right, let's try the next one. Solve each equation or inequality. Here, we have the natural log of 3x equals 0.5. We're going to solve for x. Here we have an equation where we have a logarithm on one side and none on the other. We've known how to solve these type of problems actually from one of the earlier lessons, I think lesson 3. Remember, this is just the same as. I'll write it in. You don't normally have to write it in. But natural log is log base e. So you're solving this equation. You're solving for log base e of 3x equals 0.5. Use the scorpion move, if you guys remember that. Just write it in its other form. Okay, that means 3x equals e to the 0.5 power. All right? So divide both sides by 3. E to the 0.5 power is a number. Because remember, e is a number. So if you divide both sides by 3, you get x equals e to the 0.5 power over 3, which is approximately 0.5496. All right, last one. Let's look at this problem down here. The natural log of 2x minus 3 is less than 2.5. All right, let's solve for x. This is an inequality this time, but we have a logarithm on one side of the equation. So again, we're going to write it in its other form. Okay, we're talking about base e here. Remember, this is log base e. All right, so we can write this as, imagine it as log base e of 2x minus 3 is less than 2.5. Now, remember when we're dealing with inequalities, this symbol stays oriented with that part right there. So the 2x minus 3 and that symbol are going to stay with the same orientation. All right, so let's write that first. Let's just write 2x minus 3 is less than. So that stays the same. Because when we write it in our other form, the base e and the exponent 2.5. That's how it should be written. All right, now, base e to the 2.5 is a number. We're trying to isolate the x. Let's add 3 to both sides. 2x is less than e to the 2.5 power plus 3. All right, and let's finish up by dividing both sides by 2. If you divide both sides by 2, you get x is less than e to the 2.5 plus 3 all over 2. Now, you could solve this with a calculator. All of this right here is something you can do in your calculator. Be careful with how you enter it, but when you're done, you should have x is less than 7.5912. Okay, now, be careful. Be careful. This is one of those less thans. And if we look back up here, if you guys remember, this value, the beginning, 2x minus 3, can't be 0 or negative. And we're talking about being less than 7.5912. So we have to clarify that a little bit more. Right? Take our value in green there, write it over here. Remember, 2x minus 3 must be greater than 0. All right? So 2x must be greater than 3. X must be greater than 3 over 2. All right, so when you take that into account, our final answer is x. Oops, let's fix that. That didn't look good. Is x is greater than 3 over 2 and less than 7.5912. And that's the answer for that last problem. And that keeps the number there in the log from being 0 or negative, but it also keeps the equation true. All right. So I'm going to ask you guys questions about this video on Monday. We're going to do practice problems. If you haven't already, watch the other video. It talks about how E is derived. See you later.